Ladies and gentlemen, I got called out of my slumber because someone targeted my math skills. And so I'm putting them to the test. And I am going to show this person that I can do what they claim. Let's back up. Let's just back up here and talk about where this all came from. For those that don't know, I'm a bit of a gamer. I'm a bit of a gamer myself. I actually do something called speedrunning, which is beating video games as fast as possible. I actually, at one point in my life, held a world record. Which was pretty cool. Pretty cool. I actually still hold the world record. It's pretty cool and sick, but that's not the point of the video. The point of the video is I meet people doing stuff like that, and one of my people that I compete with decided to throw a little something funny because they know I'm a math major. They decided to send a little bit of a meme over Discord that we can see says, "Oh, you're good at calculus? How about you calculate a way to get a girlfriend?" And so Mr. Baby Cow number 8885. I'm going to do that, okay? I'm going to do that now. I'm going to use calculus, and I am going to calculate the most optimal way, not only how to get a girlfriend, but the most optimal way to find a girlfriend. Dude, I got so excited I had to sneeze, okay? This video is crazy. I mean, I will be honest. I will be honest and come clean. I did find this problem online, and I did follow along with the person who wrote the article on this idea of a problem. And I'll leave that article in the description if you're so interested in reading it, because I know all of you are. But without further ado, I present to you the girlfriend equation. Sit back, relax, and enjoy. There's going to be a lot of great math lessons along the way as I tell a beautiful math story that ends in using calculus to figure out how to get the best girlfriend. Without further ado, let me show you the math. All right, let's go ahead and set up this problem and see what this problem really entails. So, for an example, let's say you're going to meet 3 different people in your life, and we're going to call them person A, person B, and person C. And let's go ahead and rank them. So A is the best person, B is the second best person, and C is the third best person. So your goal is you want to marry A in this situation. And I'm also going to go under the assumption that you're only going to date one of them at a time. I mean, it's your life. If you want to date multiple people at a time, that's great, but that's not really going to work for this video. So I'm going under the assumption that you're dating one person at a time to find the best person. That being said, what are all of the possible combinations of meeting people? Well, you could just go person A, person B, person C. You could flip the order of C and B. You could start by meeting person B and then meet person A and C. Or you could go B, C, A. You could meet person C and then A and then B. And then you could meet person C and then person B and then person A. Those are all the different ways that you can meet these people, right? Now, let's just say that your algorithm is you want to marry the first person that you meet. If you marry the first person that you meet, then we're just looking at this first step, correct? Now, what is the probability that you marry the right person? Right person, but in the case that, A is the best, you want to marry A. What is the probability that you marry A? Let's put it that way. Well, there's 2 different combinations that have you marrying A in the first step. So 2 possible combinations divided by 6 possible total combinations means that you have a 1/3 chance of marrying the right person if you just marry the first person you see. But that seems a little far-fetched, and as say you meet 10 people in your life, 15 people in your life, well, then it goes down to 1 in 10, 1 in 15, 1 in 20. Your odds keep getting worse and worse and worse for you. So this is not going to be a method that's going to work in the long run. So what is a method that will work in the long run? Well, let's explain a method that could work in the long run, and the method that we'll look at in this video for this algorithm. You intentionally reject the first person that you date, and then you marry the next best person. You marry the next person that is better than the person you rejected. So what does that look like? Well, in our example here, for our first step, we would reject A. And then we would ask ourselves, is B better than A? No. So we have to reject B. Then we get to C. Is C better than A? No. So we reject C. So we can see that in this special combination, we actually would be single our entire life. And that same would be true anytime we start with A. We would have to be single our entire life because no person's better than A. But what about if we start with B? Well, we're intentionally going to reject B, and the next person we date is A. Is A better than B? Yes. So we marry A, and we're done looking. Okay, we reject person B, we go to person C. Is person C better than person B? No. So we reject person C and go to person A. Is person A better than person B? Yes. So we marry person A. Reject person C. Is person A better than person C? Yes. So we marry person A. Reject person C. Now this is the trick. Is person B better than person C? Yes. And so by that logic, we would have to marry person B. Now in this case, if we follow this algorithm, what is the probability that we marry person A? Well, there's now 3 different paths where we marry person A, which means that our probability is 3 over 6 possible combinations, which means that we have a 1/2 chance of marrying A. So this method has 2 major benefits. Major benefit number 1 is we actually have a higher probability of marrying the right person. If we siphon off the first set of people as like a test set and base everyone afterwards off that test set. So that's benefit number 1, is our probability of finding the right person goes up. And the number 2 reason is we also have less error. Notice in this case that we only actually marry the wrong person 1 time, because we didn't marry anyone in this case. Versus if we just married the first person we saw, well, there's 4 possible cases where we marry the wrong person. So we've got error going down, we got probability that it works going up. Things are working out for us with this method. But it's not like everyone's going to only meet 3 people in their life. So let's see if we can generalize this model a little bit. And here's how we can do that. Let's say we follow this model, and we might want even a bigger test set. Not necessarily just one person that we intentionally reject, but maybe we reject like 3 people, 5 people. I don't know. But we're going to reject some amount of people. I'll put ... because I don't know how many. But we're rejecting some people, for sure. Then we'll have our first person that we actually date and evaluate that we marry. And then maybe some time will go on, and maybe the actual person we should marry is right here. And maybe some time will go on, and there will be the last person. Now, what does this look like? Well, we have our, in red, what I call over here our test set. Right? Then we have right here our, I guess we can call it like the right person, right partner, whatever that means, like right in quotes, sure, okay. And then this right here is the last person. So that means, let's say that in total we have n people. Okay? There's n total people we'll see in our life as potential partners. And let's say that we start evaluating people at the rth person, which means how many people are in the test set? Well, there must be 1 minus r people in the test set, because we're starting at the rth person. So everyone before that, it's r minus 1 people. I always want to flip it because I think probabilities. We're going to get to probabilities in a second, so pardon my confusion. But there's r minus 1 people in the test set if we're starting to look at the rth person. And let's say that the right person is the ith person. This is the right partner we want to marry. And then this is just the last person, is just the nth person. So, what is our goal? Our goal is to find the value r minus 1 over n. Pause. What does that mean? R minus 1 is the number of people in our test set. N is the total number of people. So this is just the percentage of people that are in our test set. So basically, we're asking how many people should be in our test set such that we maximize P of R, where P of R is the probability that we find and marry the best person. Given we reject the first r-1 people. So that's our goal. Our goal is going to be to maximize this probability function. Well, in order to maximize that probability function, we need some numerical way of representing that probability function. So let's talk about how do we represent that probability function numerically. Well, what does that mean as a probability? The probability that we find and marry the best person given we reject the first r-1 people. Well, say we get to person I, like we had in our drawing up here. We want the probability that person I is selected and person I is the best person. Okay? Now, we can rewrite the phrasing of this a little bit. If you've taken a stats class, you know that if you have the probability, if you have the probability of an event A and an event B, then that's equal to the probability of the conditional probability of events A and B times the probability of event B. Now, what does a conditional probability mean if you've never seen that before? A conditional probability simply means the probability of event A given that event B has happened. So it's basically, that's why it's called a conditional probability, because you're conditioning on the fact that something else has already happened. So that means we can rewrite this as the probability that person I is selected given that person I is the best, and then multiply it by the probability that person I is the best. Now, numerically, what are these values? Well, what is the probability that person I is the best? Well, we've got n people, and only one person can be the best. So the probability that person I is the best, that's just 1 over n. Easy peasy lemon squeezy. But what about the probability that that person I is selected given that person I is the best? Well, we can go back to that diagram from before, but we've got to change it a little bit. Because we have people in our test set. We have our first person that we check, right? That's still the rth person. There are still, I always want to do one myself, r-1 people in the test set. And then when we find the right person, the ith person, we stop, even if there's more people afterwards, right? Because once we find the best person, we're done. So ith is the best person. Okay? But since we know that the ith person is the best person, will we always pick the ith person? And the answer is no. Because if we have another person in between the rth person and the ith person, including even the rth person, that is simply better than everyone in the test set, but is not better than the ith person, well, we got a problem because we're going to pick this person then. So how do we ensure that this person is in this test set so that we don't pick this person on accident? Well, that's pretty easy. We just have to make sure that this person that is between the rth and the ith person is actually just in the test set. Which means that we have an expression of r-1 over I-1. That's how we can get around that. And so, what we have is, that means this is r-1 over I-1. And so, we get that P of r is equal to r-1 over I-1 times 1 over n. Or that P of r is r-1 over n times I-1. Now we're done, right? Well, not quite. This is actually not true. Because This only accounts for the ith person. But there's a bunch of people that we're wanting to meet. And so we don't want to pick it for one specific person. In order to calculate the probability of the best girl, we must consider every single girl, I should clarify language. If we want to calculate the best partner out of all of our pool of people, we have to sum this value over every person in the pool, which means that a true probability function is going to be the sum. That's what this fancy little sigma is. It's called sum. From I equals 1 to n of r minus 1 over n times I minus 1. That way we can do it for every single person in our pool of people. Okay. Well, there's also something else we have to keep in mind. We're summing over every single person in the pool. But remember, we are intentionally rejecting the first r minus 1 people. So the first r minus 1 people, the probability that we pick them is going to be 0. So we can account for that, actually. We can split up this sum, right? We can split up this sum into the sum of starting at 1 and going to r minus 1 of this plus the sum going from r to all of the people of r minus 1 and I minus 1. But, right, we said doesn't matter what the value of this function is, we're going to reject all of these people. So this is going to go to 0. And you'll also notice that this is a constant. So we can pull that out of our sum. So we have a new p of r, and that's equal to r minus 1 over n times the sum from I equals 1 to n of 1 over I minus 1. Now, as we go on further in this problem, the author makes a specific generalization. And the author says that they are going to follow the generalization that... I'm going to write this down. They are going to follow the generalization that the sum from I equals 1 to r of 1 minus I, that is going to be pretty much the same thing as the natural log of r. Now, I'm going to be honest. That felt a little bit weird to me without being proven. And I plugged it into my calculator for very large values, like up to, I think I did up to 10,000. Where I set r to 10,000. I ran this 10,000 times. And then I calculated the natural log of 10,000. And it pretty regularly was about 0.5 less, or the value of the natural log of r was pretty regularly about 0.5 less than this sum. So, for all intents and purposes, I'm down to say it's roughly that, but just be aware that we probably shouldn't be making... I feel like we probably shouldn't be making this generalization. But it does simplify this problem very nicely, and so for the sake of showing off cool math knowledge and telling a math story, we're going to let this generalization go through. Why do we want this generalization to go through? Well, let's go ahead and do some rewriting of P of R. And what rewriting of P of R are we going to do? Well, we're going to notice that we're going from 1 to n. Let's say, or sorry, this should be R. We're going from R to n. Here, I made a mistake there. Does that make sense? I think, what did I have before? I think it was I. Yeah, I said I equals 1. Nope, so then I should be R, not I equals 1. So what we're going to do is we still have this r minus 1 over n coefficient, but we're going to just start at 1 less. We're going to backtrack 1. But if we backtrack 1 here in order to have the same value of the sum, we have to backtrack our n step by 1. So all I'm doing is taking our starting, and we're shifting it backwards. That's all I'm doing. And if I shift backwards,
that means that I get 1 over I.
If I shift the starting values backwards.
And now we're going to do a little bit of finagling with our sums. So we get r minus 1 over n in parentheses. We are going to do a sum starting at 1 and going all the way to n. Starting at 1 going all the way to n minus 1, of 1 over I.
Now, think about that. Think about our bounds in our previous step. We are adding more values.
Which means we need to subtract away some values. And so we're going to have to subtract away a sum. But what do we subtract away? Well, we want to subtract all the extra values would be all the values from 1 to r minus 2. So subtract away r minus 2.
And now you see why this generalization is going to be really nice.
Because now what I can do is I can say that this is equal to, we still have that r minus 1 over n, but this is now going to turn into, and I should clarify, this is our generalization step. It's going to be
roughly, it's going to be a little less in reality, but for all intents and purposes, we'll say it's the natural log of n minus 1, right? Because up here, we just take the upper bound and we stick it inside the natural log. That's the generalization we're making. So stick the upper bound into a natural log. Natural log of n minus 1 minus the natural log of r minus 2. Now, what can we do with that? Well, if you know your logs, then you know that if you have a log minus another log, then you can have one log of the first divided by the second.
So this is times the natural log of n minus 1 over r minus 2.
Now, the author says something here that I don't think is true, but maybe you guys in the comments can help prove me wrong.
Oops, I just dropped my pen under my bed. That's embarrassing.
Yoink!
Oh, where'd you go, buddy? Oh, I really shoved it under the bed, excuse me. Ka-dink.
Okay. Let's take a look at this. So, the author makes a generalization that I'm pretty sure is wrong. But, again, for the sake of telling a math story, we'll go ahead and go with it.
The author makes the generalization that as n goes to infinity, you are going to end up with this function. That it is going to be generalized to about r over n times the natural log of n over r.
Now, I personally don't see how that's true as n goes to infinity, because, well, if you've taken calculus, if you think about what happens as things get really, really big, well, the denominator's going to get really, really big, and this is a constant, so the denominator's going to get really, really big, which means this is going to just go to 0, which means the whole thing's going to be 0. Hard for me to believe that that's true. I think what the author was trying to do
was get rid of this minus 1, minus 2.
And I think the argument that the author was trying to make, again, this is me writing the general story and trying to understand it, but from what I understand, it feels like the author is trying to make the claim that as you get really, really big, as you keep adding more people to your pool,
this minus 1, like subtracting
a constant from another constant is just not going to matter as you get more people in your pool of people that you can potentially marry. I can understand that. This is not the phrasing to make that happen, in my opinion. But if that's what you're trying to claim,
and you do put the generalizing symbol that is listed in the article,
fine. We'll pretend that that's what you meant to say
when you said this,
and we'll move on. The reason we want to make sure that we end with this is because this looks really, really pretty. Because what do mathematicians do? They like to rename things to different things.
So let's say that we let x equal r over n.
Okay.
Then we get that p of r is equal to x times the natural log
of
times the natural log of 1 over x, right? Because n over r is the reciprocal of r over n. So what's the reciprocal of x?
It's 1 over x.
Okay.
And
what we can do is, right, remember we have some rules. We can rewrite this as, well, if it's a fraction, then we can turn it into a negative exponent.
that's definitely allowed in math.
And what we can do is then we can stick that negative exponent out front. So now we have this really nice function that we can use.
Because now, remember, like I said, why are we even doing all of this math?
We're doing all this math because we needed to figure out what
P of r is, but we're not done. Because now what we have to do is we have to figure out how to maximize this function. Well, how do we find maxes and mins? We do calculus, baby.
So,
remember, to find maxes and mins from your calculus days, you need to take the derivative of this function and set it equal to 0 to figure out where potential maxes and mins will occur. Now, I will say that if you were to plot
this function in your graphing calculator,
and you can actually do this in your graphing calculator, this really is what
what the function looks like, you get something that looks a little bit like this.
And so if you get something that looks a little bit like
This, well, it's pretty clear that you're really only going to have
one maximum, right? Remember, normally you're supposed to check that it's a max or a min, but we can pretty safely assume from looking at the graph that we know that's going to be, that we know that it has to be a max. Now, you're probably sitting here thinking, come on, Trevor, put this in your T84 Plus color edition so we don't have to do calculus. But hey, I'm a man of my word. I said I would do calculus to find the optimal girlfriend, and by golly, we're going to do calculus to find the optimal girlfriend. So here we go.
What does that look like? Well, if we take the derivative with respect to x, I also call it's now a p of x, I guess.
I was messing with the numbers, but I guess it's...
Or, no, it is p of r. But we're going to take the derivative, whatever, we'll just leave that off. We'll take the derivative with respect to x of negative x times the natural log of x. Well,
we've got a product rule in our hands.
So it's the first times the derivative of the second, derivative of natural log x, 1 over x, plus the second, natural log of x, times the derivative of the first, negative 1. So that derivative is equal to, looks like negative ln x minus 1, because these cancel.
Okay, we have to set that equal to 0 to find our max.
Okay, well, looks like we get negative ln x equals 1, which means ln x equals negative 1. And remember, ln x, that's the same thing as log base e of x equals negative 1, which means that x is equal to e to the negative 1.
Remember, logs, the answer to a log is an exponent. So to undo it, what's inside is the answer to an exponent problem. So we can rewrite it like that. Now, what's e to the negative 1? Well, pull out our T84 Plus Color Edition. E to the negative 1 looks like is roughly
0.3679, which means roughly 37% if we were to translate it to a percent.
Which was our ultimate goal at the end of the day. What does that mean? Well, that means you need to make your test set of people, of all n people you meet, your test size of people needs to be roughly 37%. You need to have roughly 37% of people that you meet be in your test set in order to have the highest chance of maximizing the potential that you will you will marry the best person. So there you go. I used calculus to maximize my girlfriend potential. Now, if you're a mathematician and any of this felt sus, I mean, when I was reading the article, I felt like there were some things that were a little overgeneralized for me. So if you want to leave your solutions in the comments as to what was wrong in this video, I would greatly love to appreciate it. But sometimes it's just fun to tell a story with math. And even though the math can be wrong, sometimes it leads to a really cool story. Oop, it's over here. Sometimes it leads to a really cool story and some really cool learning math objectives. So there you go. I used calculus to maximize my girlfriend potential. Thank you so much for watching, and I'll see you in the next video.